You know how when you follow a recipe, you take a few simple things, maybe add some heat, and end up with something totally new? Well, today we're doing just that, but on an epic scale. We're stepping into what's basically the world's most important chemical kitchen to cook up ammonia. And the recipe we're going to follow, it's called the Haber process. And believe me, this thing literally changed the world. So, here's what's on the menu today. First, we'll get properly introduced to our final dish, ammonia. Then we'll check out the core ingredients. After that, we dive into the recipe itself. And trust me, it's pretty high stakes. We'll even uncover a secret spice, the catalyst, and then finally figure out how to plate it all up, or, serve the final product. All right, first things first, let's meet the star of our show. I mean, before we get our hands dirty in the kitchen, we should probably know what it is we're trying to make, right? So this is ammonia, or NH3 if you're feeling scientific. It looks simple, just one nitrogen and three hydrogens, but don't let that fool you. It's a colorless gas, but it has this super sharp, pungent smell. You definitely know it if you smelled it. And the way we make tons of it, the method that really changed everything, is the Haber process. And that is exactly the recipe we're breaking down today. Okay, so like any good recipe, it all starts with the ingredients. For the Haber process, we actually only need two things. But here's the catch. Getting the amounts, the proportions, exactly right is absolutely crucial. So here are our two key ingredients. First up is nitrogen, which we literally just pull from the air all around us. Pretty convenient, right? The second is hydrogen. But the real secret, the part you absolutely can't mess up, is the ratio. You need exactly 1 part nitrogen to 3 parts hydrogen. Get that mix wrong and the whole thing just doesn't work. It's a total bust. All right, so we've got our ingredients and they're mixed in that perfect 1-to-3 ratio. Now for the fun part, the cooking instructions. And let me tell you, this is not your average kitchen recipe. We're talking about some seriously extreme conditions here. First up, heat. And I mean a lot of heat. We need to crank the temperature up to somewhere between 450 and 500 degrees Celsius. Just to put that into perspective for you, your oven at home probably maxes out around 250 Celsius, if that. So we have to get things almost twice as hot just to get this party started. Okay, after the heat comes the pressure. And we're not talking about just a little bit of pressure. No. We need somewhere between 200 and 900 atmospheres. That is an insane amount of pressure. It's like being crushed at the bottom of the deepest parts of the ocean. We're basically squeezing these nitrogen and hydrogen molecules so hard that they have no choice but to react. But, there's always a chef's note in the recipe, right? A little warning. And this one is critical. While pushing the pressure higher is great for the chemical reaction, you hit a point where it's just too much. If you go too high, the plant itself, the actual pipes and tanks, well, they might not be able to handle it. So it's this constant, delicate dance between getting the best chemical reaction and, not blowing the whole place up. So you'd think with all that crazy heat and pressure, we'd be good to go, right? Well, not quite. The reaction would still be way too slow to be useful on an industrial scale. And that's where our secret ingredient comes into play, the catalyst. You can think of it like a chemical matchmaker or a shortcut that makes this whole thing actually work. And this secret ingredient is actually a two-part deal. The main event, the catalyst itself, is just finely divided iron. It basically gives the nitrogen and hydrogen a place to meet up and react. But then the iron has a little helper, a promoter, called molybdenum. Now, the promoter doesn't speed things up on its own, but it makes the iron catalyst way more effective. It's like the ultimate hype man for the main star. Okay, the cooking is done. But here's the thing. Our reaction chamber is now this big mix of the stuff we want, the ammonia, and a bunch of leftover nitrogen and hydrogen that didn't react. So the final step in our recipe is separating the good stuff from the leftovers. So how do we actually do that? Well, it turns out we have two really clever ways to do it, and they both take advantage of ammonia's unique personality, so to speak. Method 1 is called liquefaction. You just cool the whole gas mixture down. At minus 33 degrees Celsius, the ammonia says, "I'm done," and turns into a liquid, which you can just drain away. But the nitrogen and hydrogen, they stay as gases until it gets way colder. The other method, just use water. Ammonia loves to dissolve in water. I mean, it's super soluble. The other two gases, however, barely dissolve at all. So you can literally just wash the ammonia right out of the mix. Pretty smart, huh? And there you have it, the complete recipe. That's how we take the air around us and turn it into ammonia, the key ingredient in the fertilizers that feed billions of people on this planet. It's wild when you think about it. All that extreme heat, that crushing pressure, that secret catalyst, all just to unlock nitrogen from the atmosphere. It really makes you stop and wonder, doesn't it? What other incredible power is just waiting to be unlocked from the simple, invisible stuff that's all around us every single day?